Okay, let's move on to the actual rules themselves. Basic derivative rules. Dum, dum, dum. First thing to be aware of is just some notation. There are several different types of notation that actually mean the same thing. Let's say that we have an equation, y equals some function of x, or whatever. dy dx means the derivative of y with respect to x. So that means that we're going to use the rules that we're about to learn to just find something that's called the derivative of y with respect to x, and this is going to be what we get. So we're going to end up with dy dx, the derivative of y with respect to x, equals some equation. There's another way to say basically that exact same thing. Let's say that we have some equation f of x equals 3x plus 2. F prime of x, that little symbol is called a prime, just means the derivative of f of x. These two things are saying exactly the same thing, and our final answer will both be this equals whatever, this equals whatever that derivative ends up being. I want to contrast these two notations though with a third one. D dx of 3x plus 2. I'm going to number these so that we keep them a little clearer. This is different. This dy over dx is different from d over dx. Specifically, this is a command to take the derivative of what's to the right. So notice, we're going to have situations where we write dy dx equals something, f prime of x equals something, but we are not going to have situations where we have d dx equals something. This is active. It's telling us a command. We're going to take the derivative of what's right here. So be careful with those different notations. Now, finally, the basic rules. The first one is called the constant rule. And we're going to look at where these rules come from in the limits unit, but right now I just want you to be able to do the mechanics fluently. The power of calculus was that rather than making everyone do this the long way, it developed a series of shortcuts that could be used on their own independent of their origin. It's really important to learn the origin. Most classes do the origin first and then go into the rules. We're actually doing the rules first. I want you to be really fluent in how to use them, and then we're going to go back and look at where they came from in another unit. So the constant rule says, let's say that we are told to take the derivative of some constant c. So this is just a constant, some number. Not a variable, a number. If we are told to take the derivative of a number, that always equals 0. Every single time. So, if I say take the derivative of 3, that equals 0. Here, I'll number these. If I say f of x equals 10, find the derivative of f of x. The derivative of a number is 0. if I have y equals 10, and I want to find the derivative of that function, 0. Anytime that we have a number, a constant, we're taking the derivative, it equals 0. And this actually makes quite a bit of sense if we look at graphing a constant function. A constant function just means like y equals 10 is just a flat line. The slope of this line, it's a flat line. The slope is always 0. So, try this one on your own. Take the derivative of square root of 36. This is just a number. The derivative of any constant number is 0. There we go. This is also true, incidentally, of numbers like pi or 1,964,000, whatever. As long as it's just a number, derivative is 0. Check. Once we get variables in there, things get a little more interesting. Next up is the power rule. That says that if we take the derivative of a variable to some power, so this is a variable x, n is just some number, what we're going to do is we're going to bring down this exponent, and then we're going to subtract 1 from the exponent. So, to give you an example, if we're told to take the derivative of x squared, I'm going to bring down the 2, and then I'm going to subtract 1 from the exponent. So 2 minus 1 is 1, or x to the first power, which is the same thing as 2x. If I'm told that I have function f of x equals x to the third, and I want to find the derivative, I'm going to bring down the exponent, subtract 1 from the exponent, and there we go. So try this one. Let's say we have the function y equals x to the fourth. I want you to find the derivative of that. Okay, what we do is we bring down the exponent, subtract 1, and there we go. Ta-da! This is really the main rule that's at the heart of a lot of taking the derivative. The other ones that we're going to go over are kind of just little variations on it. So I want to look for a second at why this makes sense. Let's say that we've got some function, let's say this is like x squared or something, and we're trying to find the derivative. Well, we know that right here the slope is 0, so I'm going to graph the slope just at that 0. So this is f of x, this is the derivative. Here it's a little negative, here it's even more negative, here it's a little positive, here it's even more positive. That x squared function turns into a linear or just an x function. Basically that's what we see here. This squared turned into a linear function. Likewise with something over here, if we started off with x to the third, and we're finding the derivative, right here the slope is 0. Here it's a little bit positive. Here it's also about the same amount of positive. Here it's really positive. Here it's a really positive slope. And it forms that nice parabola, x squared shape. You wouldn't necessarily see it immediately from doing all these graphs and see that pattern immediately, but if we look at it, it does line up with what we observe from the graphs. Basically, whenever we take a derivative, the power reduces by 1. X squared to x to the third to x squared. So the next one up is called the constant multiple rule. And what that says is it says that when we take the derivative of some constant times f of x, that's the same thing as just multiplying that constant times the derivative of f of x. Really all this says is that any number, any constant here, is just along for the ride when we do differentiation. So, for example, let's say we're taking the derivative of 3x squared. That's the same thing as doing 3 times the derivative of x squared. That 3 is just along for the ride. So we've got that 3, bring down the 2, and subtract 1 from the exponent. And there we go. So to give another example, let's say that f of x is 1 over 93 x to the third, and we want to find the derivative of f of x. This 1 over 93 is just along for the ride. What we're going to do is we're going to take the derivative here, bring down the 3, subtract 1 from the exponent, and there we go. Now we'll just multiply here. And that'll cancel to be 1 over 31 x squared. Any number in front, just along for the ride. Try this one on your own. Take the derivative, 6 x to the fifth. Okay, that 6 is just along for the ride. We bring down the 5, subtract 1 from the exponent,